The night sky holds more questions than answers. For every star you see, a deeper cosmic mystery defies explanation. These are the 30 unsolved questions that keep astrophysicists awake at night, from the ghostly presence of dark matter to the universe's ultimate fate. By the end of this, you will understand the biggest gaps in our cosmic knowledge and how they might reshape reality itself. We will explore why galaxies spin too fast, what force is ripping the cosmos apart, and if we are truly alone. What do you think is the universe's most profound secret? Galaxies spin with such ferocious speed that their stars should be flung into the void, yet they hold together, bound by an invisible hand. This ghostly presence, dark matter, is the universe's most pervasive secret. The story begins in the 1930s with an astronomer named Fritz Zwicky. He studied clusters of galaxies and found something deeply unsettling. The galaxies were moving far too fast. According to the laws of gravity, the visible mass in the cluster was not nearly enough to hold them together. They should have flown apart. The only explanation was that something we cannot see was providing the extra gravity, a hidden mass he called dunkle materie. Decades later, astronomer Vera Rubin provided stunning confirmation. By carefully measuring how fast stars orbit the centers of spiral galaxies, she found the same bizarre result. Stars at the outer edges of galaxies move just as quickly as those near the center. This defies all expectations. Think of our solar system, where planets closer to the Sun orbit much faster than those farther out. In a galaxy, if only the visible stars and gas were present, the outer stars should be moving much more slowly. The fact that they are not means that every galaxy is embedded within a gigantic, invisible sphere of dark matter, a halo that holds the entire structure together with its immense gravitational pull. We now believe this unseen substance makes up about 27% of the entire cosmos, outnumbering normal matter by a factor of 5 to 1. So what is it? The leading idea is that it is a new type of elementary particle, one that rarely, if ever, interacts with light. Physicists have built incredibly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch a fleeting whisper of a dark matter particle passing through. They have proposed candidates with names like WIMP, or weakly interacting massive particles, and actions, hypothetical ultra-lightweight particles. Yet so far the detectors have remained silent. Another line of evidence comes from gravity itself. Massive objects like galaxy clusters warp the fabric of space-time, bending the light from more distant galaxies behind them. This effect, called gravitational lensing, allows us to map the distribution of dark matter. In one of the most dramatic examples, the Bullet Cluster, two galaxy clusters collided. The visible gas, hot and turbulent, slammed together and slowed down, but the dark matter inferred from the lensing maps sailed right through the collision, completely separate from the normal matter. This proved dark matter is not just a misunderstanding of gravity. It is a real, physical substance that does not interact with anything except through its gravitational pull. What if it is even stranger than we suppose? Could dark matter have a faint, unknown force acting on it? Or could it be a sign that our understanding of gravity on cosmic scales is fundamentally incomplete? This mystery is the foundation upon which the entire cosmos is built, and its solution will redefine our place in the universe. If dark matter is the ghostly anchor holding galaxies together, then dark energy is the phantom force tearing the cosmos apart. This discovery was so shocking it upended our entire view of the universe's fate. For decades, astronomers assumed the expansion of the universe, set in motion by the Big Bang, was gradually slowing down thanks to the relentless pull of gravity. Everything was expected to eventually collapse back in on itself or coast to a gentle halt. Then, in the late 1990s, two independent teams of scientists made a breathtaking observation. By studying distant stellar explosions called Type 1 a supernova, which act as standard candles to measure vast cosmic distances, they found that these beacons were fainter and thus farther away than they should have been. The inescapable conclusion was that the expansion of the universe is not slowing down at all. It is accelerating. Something is forcefully pushing galaxies apart, and this discovery earned the Nobel Prize in Physics in 2011 for leaders of the teams, including Adam Rees and Saul Perlmutter. This mysterious repulsive force was dubbed dark energy. We now calculate it makes up a staggering 68% of the entire cosmos, the dominant component of reality. So what could it possibly be? One of the oldest ideas comes directly from Albert Einstein's own equations. He introduced a fudge factor called the cosmological constant, a sort of innate energy inherent to the fabric of empty space itself. This vacuum energy would have a repulsive gravity pushing the universe outward. Einstein later called it his greatest blunder, but it may have been his greatest prescience. Another theory suggests dark energy is not constant at all, but a dynamic force field called quintessence that could change over time, potentially even weakening or strengthening. Then there is the haunting possibility that it represents a new type of physics, a sign that Einstein's theory of general relativity breaks down on the largest possible scales. We see its fingerprints everywhere. The Planck satellite's detailed map of the cosmic microwave background, the afterglow of the Big Bang, shows a specific pattern that only makes sense if dark energy exists. This energy dictates the ultimate destiny of everything. If it continues to accelerate the expansion, as all evidence suggests, the universe faces a cold and lonely end known as the Big Freeze. Over trillions of years, galaxies will be pulled so far apart that the sky will go black, star formation will cease, and the cosmos will become a vast, dark, and empty void. This leads to one of the most perplexing puzzles of all, the coincidence problem. Why now? Why does dark energy's dominance happen to occur at the precise cosmic epoch when we, intelligent observers, exist to see it? Is it merely a strange accident or a profound clue? Dark energy is the central question of our cosmic destiny, a silent, overwhelming force whose true nature remains just out of reach. The accelerating expansion driven by dark energy points back to a single, unimaginable starting point. How did everything, the entirety of space and time, first come into being? The dominant story is the Big Bang, a theory describing a moment of immense creation from a state of infinite density and temperature, a singularity. But the term itself is a misnomer. It was not an explosion in space, but a rapid emergence of space itself, expanding and cooling from that initial hot, dense state. For all its success, the Big Bang theory leaves the most fundamental question unanswered. What triggered this cosmic genesis, and what, if anything, came before? To solve the puzzles the standard Big Bang left behind, physicists like Alan Guth proposed a spectacular addendum called cosmic inflation. This idea suggests that in the first fleeting fractions of a second, the universe underwent a period of hyper-fast exponential expansion, smoothing it out and seeding all future structure. Think of blowing up a balloon that has a few tiny, random wrinkles on its surface. As the balloon inflates to an enormous size, those tiny wrinkles become vast, continent-sized features. In the same way, minute quantum fluctuations, tiny ripples in the energy field of the infant universe, were stretched to cosmic proportions by inflation. These ripples became the gravitational seeds for everything we see today, the eventual galaxies and clusters of galaxies. This theory elegantly solves the horizon problem. Why does the universe look so uniform in all directions? Distant regions on opposite sides of the sky have the same temperature, yet in the standard Big Bang model, they never had time to contact each other and reach this equilibrium. Inflation solves this by stating that these regions were indeed in close contact before the rapid expansion blew them apart. Evidence for this comes from the cosmic microwave background, the faint afterglow of the Big Bang. Missions like the Planck satellite have mapped its minute temperature variations with exquisite detail, finding a pattern that matches the predictions of inflation almost perfectly. It is a fossil imprint of the universe's quantum origins, yet this profound idea raises even deeper questions. What powered inflation? What is the inflaton field that drove this stupendous expansion? The search for direct proof continues, most notably in the hunt for primordial gravitational waves. These ripples in space-time, generated by the violent throes of inflation, would leave a distinct curl-like pattern in the cosmic microwave background. Detecting them would be like hearing the echo of creation itself, but so far they remain elusive. Alternatives to a single Big Bang exist, such as the cyclic model, which proposes a series of universes born from collisions of higher dimensional membranes, a perpetual cycle of birth, death, and rebirth. The great Stephen Hawking suggested that asking what came before the Big Bang might be like asking what is north of the North Pole. In his view, time itself began at that singularity. So we are left standing at the edge of known physics, peering into the ultimate mystery. What set the cosmic clock ticking in the first place? The answer may lie not in a moment of creation, but in a fundamental rewrite of reality where time, as we know it, simply did not exist. That ultimate beginning sets the stage for an even more profound ending. The fate of the entire cosmos hinges on a delicate and invisible balance, a cosmic tug of war between the outward push of dark energy and the inward pull of gravity. We are left to wonder if the universe will end in ice, fire, or something even more strange. The most widely accepted forecast based on our current measurements is the Big Freeze, also known as heat death. In this scenario, dark energy remains dominant, relentlessly accelerating the expansion of space. Over trillions of years, galaxies will recede from one another, their light fading as space stretches. Star formation will eventually consume all available gas, and the last stars will flicker out. The universe will become a vast, ever-cooling sea of dispersed particles and dead stellar remnants. Even the black holes, the most durable objects, are not eternal. Through a process predicted by Stephen Hawking, they slowly leak radiation and evaporate over almost unimaginable timescales. The final state is one of maximum entropy, where energy is evenly distributed and no more work can be done, a static and silent end. But this is not the only possibility. What if dark energy is not constant? Some theories, like quintessence, suggest it could evolve. If it were to weaken and allow gravity to regain the upper hand, the expansion could slow, halt, and reverse. This would lead to a big crunch, a mirror image of the Big Bang where the entire universe collapses back into a state of infinite density. Everything we know, every galaxy and atom, would be drawn together into a single, fiery point. This dramatic finale raises another tantalizing question. Could a big crunch simply trigger a new Big Bang, birthing a new universe in an endless cycle of death and rebirth? This cyclical model offers a poetic alternative to a single, finite existence. Then there is a more violent end, the Big Rip. This occurs if the repulsive force of dark energy grows stronger over time, overwhelming not just the space between galaxies, but the forces that hold everything together. First, galaxy clusters would be torn apart, then individual galaxies. As the force intensifies, stars would be ripped from their solar systems. In the final, terrifying moments, planets would be shredded, atoms would be pulled apart, and the very fabric of space-time would be ruptured. The key to which fate awaits us lies in precise measurements of the universe's expansion rate, the Hubble constant, and the precise nature of dark energy. Is its push steady or is it changing? The answer is written in the light of distant supernova and the large-scale structure of the cosmos, a puzzle we are still piecing together. The ultimate destiny of everything is not yet written, a profound uncertainty that hangs over our understanding of reality itself. Crossing that event horizon would be a one-way trip into the heart of darkness. The boundary of a black hole is not a physical surface, but a gravitational point of no return. Once you pass it, even light cannot escape. According to Einstein's theory of general relativity, your journey inward would be both terrifying and final. You would be subjected to an extreme tidal force. If you fell in feet first, the gravitational pull on your feet would be so much stronger than the pull on your head that your body would be stretched into a long, thin stream of atoms, a process physicists call spaghettification. And at the very center of the black hole lies the singularity, a point where density and gravity become infinite and the laws of physics simply cease to apply. Our understanding of space and time shatters. But what if Einstein's theory is not the final word? This is where quantum mechanics must step in, and the two pillars of modern physics enter into a violent conflict. The brilliant work of Stephen Hawking revealed that black holes are not completely black. Due to weird quantum effects near the event horizon, they slowly leak radiation and can eventually evaporate and vanish. This creates the infamous information paradox. All the information about what fell into the black hole, the unique arrangement of atoms that made up a star or a spaceship, seems to be lost forever when the black hole evaporates. But quantum mechanics insists that information can never be truly destroyed. So where does it go? One radical solution is the firewall hypothesis, which suggests that the event horizon is not a quiet boundary, but a blazing wall of high-energy particles that would incinerate anything falling in. Another mind-bending idea is the holographic principle, which proposes that all the information describing the three-dimensional interior of a black hole is actually encoded on its two-dimensional event horizon, like a cosmic DVD. The recent, breathtaking images from the Event Horizon Telescope showing the shadow of supermassive black holes are not pictures of the black holes themselves, but of their gravitational grip on the surrounding light. They confirm these monsters exist as predicted, but their deepest secrets remain locked away. Could these singularities be gateways for rotating black holes described by the Kerr metric? Some mathematical solutions suggest the singularity might not be a point, but a ring, opening the theoretical possibility of wormholes, tunnels to other points in space and time or even other universes. Yet, traversing such a passage remains firmly in the realm of speculation. The true nature of a black hole's heart is the ultimate testing ground for a theory of quantum gravity, a framework that can finally unite the vast cosmos with the tiny quantum world. What happens inside a black hole is not just a question about the fate of matter, but about the fundamental laws that govern reality itself. The fundamental laws of the cosmos are at war with each other. On one hand, you have Einstein's theory of general relativity, which masterfully describes the grand cosmic dance of planets, stars, and galaxies, painting gravity as the elegant curvature of space-time itself. It is the theory of the very large. On the other hand, you have quantum mechanics, the bizarre and probabilistic rulebook for the subatomic world, where particles can be in two places at once and reality is fuzzy until observed. These two pillars of modern physics are spectacularly successful in their own domains, yet they are utterly incompatible. When their equations are forced to meet, such as at the center of a black hole or the moment of the Big Bang, the math breaks down into nonsensical infinities. This great schism is the deepest rift in all of physics, and the quest for a single, unified theory that can heal it is the holy grail of science. The core of the conflict is gravity itself. The other three fundamental forces, the electromagnetic force, the strong nuclear force, and the weak nuclear force, are all described by quantum field theory, which involves force carrying particles like photons. Gravity, in this picture, should have its own particle, a hypothetical massless particle called the graviton. But when physicists try to describe the graviton using the same quantum rules, the calculations blow up. The process of renormalization, a mathematical trick that works for the other forces to eliminate infinities, fails completely for gravity. It is like trying to use the rules of a card game to play chess. The frameworks are fundamentally different. To resolve this, physicists have proposed radical new visions of reality. String theory suggests that the fundamental constituents of the universe are not point-like particles, but incredibly tiny, vibrating strings. The different vibrations of these strings correspond to different particles, with one specific vibration giving rise to the graviton. But for the math to work, string theory requires extra spatial dimensions, as many as 10 or 11, curled up into sizes so small we cannot perceive them. Another leading contender is loop quantum gravity, which takes a different approach. It proposes that space itself is not smooth and continuous, but is woven from a fabric of tiny, finite loops, a spin network. In this view, space is quantized, and the familiar smooth geometry of general relativity emerges from this underlying granular structure. Much like a digital photograph appears smooth from a distance but is made of individual pixels. The implications of a successful theory of everything would be staggering. It could finally solve the black hole information paradox, revealing what truly happens to information that falls in. It might explain the very origin of the universe, telling us what, if anything, preceded the Big Bang. It could even open the door to hidden symmetries of nature or provide evidence for the multiverse, a vast collection of parallel universes with different physical laws. Experiments like LIGO, which detected gravitational waves from colliding black holes, are already testing the limits of both general relativity and quantum mechanics. Every ripple in space-time is a message, a clue written in the fabric of reality. The ultimate theory would not just unite the very large with the very small. It would reveal a cosmos far more interconnected and wondrous than we have ever dared to dream. Our search for a single, unified theory of everything leads to a staggering and almost unbelievable possibility. What if our universe, with all its hundreds of billions of galaxies and finely tuned physical laws, is not unique, but merely one bubble in an infinite cosmic foam? This is the Multiverse Hypothesis, a concept that pushes the very limits of science and philosophy. The idea emerges naturally from our best theories. Eternal inflation suggests that the rapid expansion of the early universe never truly stopped everywhere. Instead, it continues in a vast, ever-expanding background, with new pocket universes constantly budding off like bubbles in a boiling pot. Each of these bubbles could have its own unique set of physical constants and laws. In one universe, the strength of gravity might be so weak that matter never clumps into stars. In another, the nuclear forces might be too strong, preventing the formation of complex atoms. Our universe, with its just right conditions for life, could simply be one fortunate ticket in an infinite cosmic lottery. This leads directly to the Anthropic Principle, a contentious but compelling line of reasoning. It suggests that the reason we observe a universe so perfectly tuned for our existence is that we could not possibly observe one that is not. In the vast multiverse landscape, we naturally find ourselves in one of the rare habitable pockets. The theoretical framework of string theory adds even more fuel to this fire. For its mathematics to work, it requires a vast landscape of possible solutions, perhaps 10 to the 500 or more distinct vacuum states. Each of these could correspond to a different universe with its own physical properties. The cosmos would be a cosmic library where every possible law of physics is written in a different volume. Yet, the greatest challenge for the multiverse is the profound question of evidence. How can we ever prove the existence of something that is, by definition, beyond our observational reach? Some scientists point to potential hints, like strange, large-scale anomalies in the cosmic microwave background. Could a cold spot in the afterglow be a bruise from a collision with another universe in the distant past? Others argue this is not true science at all, as the multiverse may be fundamentally untestable and therefore unfalsifiable. It forces us to confront the very nature of reality. Are the laws of physics necessary and universal, or are they just a bizarre, local accident? The multiverse idea does not make our existence smaller, but rather redefines our cosmic context. We are not at the center of a single, special creation, but perhaps inhabitants of one shining island in an endless, frothing sea of realities. The delicate balance that allows us to exist is written into the very code of the cosmos. Tweak any one of the universe's fundamental constants just a little, and the entire structure of reality would crumble into sterility. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself long before stars could form. If it were weaker, matter would never have clumped together into galaxies at all. The mass of an electron, the strength of the nuclear forces, even the energy of empty space itself, each is set to a precise, life-allowing value. This is the puzzle of fine-tuning, a cosmic coincidence so staggering it demands an explanation. Consider the cosmological constant, the value that governs the strength of dark energy. It is positive, driving the accelerating expansion of the universe, but it is also unbelievably small. If it were just a little bit larger, the repulsive force would have torn proto-galaxies apart before they could ever coalesce. If it were slightly more negative, the universe would have collapsed in a big crunch after only a few million years. We exist in a narrow window where this value allows for both vast cosmic structures and the long timescales necessary for life to evolve. The strong nuclear force which binds protons and neutrons together in atomic nuclei is also perfectly calibrated. If it were a few % weaker, simple hydrogen would be the only element, and no complex atoms could exist. If it were stronger, protons would bind so tightly that the hydrogen fuel in stars would burn out in a cosmic flash, leaving no time for planets to form or life to emerge. This precise tuning is shockingly evident in the very atoms that make up our bodies. The element carbon, the fundamental building block of life as we know it, should be relatively rare. In the hearts of stars, the process of fusing helium into carbon requires a remarkable coincidence. There exists a specific, resonant energy state in the carbon nucleus that allows it to form efficiently. Without this precise nuclear resonance, the stars would produce only a tiny trickle of carbon, insufficient to create planets, oceans, or living beings. It is as if the laws of physics themselves were designed with our eventual existence in mind. This observation leads directly to the Anthropic Principle, a simple yet profound idea. It states that the universe we observe must be compatible with the existence of observers. We could not possibly find ourselves in a universe devoid of life because there would be no one there to ask the question. For some scientists, this is a tautology, a simple statement of selection bias. For others, it is a profound clue. One explanation is the multiverse. If an infinite number of universes exist, each with different physical laws, then it is no surprise that we find ourselves in one of the rare habitable ones. Our universe is not special, just lucky. Another, more radical idea is the simulation hypothesis, which suggests our reality is a sophisticated computational construct, and the fine-tuned parameters are simply the initial settings of the program. Religious interpretations see the hand of a creator, but science seeks natural explanations. A more hopeful possibility is that we do not yet understand the full picture. Perhaps a deeper, underlying theory of everything will reveal that these constants are not random, but are necessarily linked, the only possible outcome of a self-consistent cosmic law. The hierarchy problem in particle physics highlights this mystery, asking why the force of gravity is so unimaginably weaker than the other fundamental forces. This vast disparity seems arbitrary, yet it is essential for a stable universe. Are we the beneficiaries of unimaginable luck, or is our existence the inevitable result of a cosmos striving toward consciousness? The answer determines whether we are a fleeting accident or a fundamental part of a much grander story. The profound silence of the cosmos is a mystery in itself. We scan the skies with powerful telescopes, listening for a signal, any sign that we are not the only conscious beings in this vast expanse, yet the universe remains quiet. This contradiction between the high probability of alien life and the utter lack of evidence is the Fermi paradox, named for physicist Enrico Fermi, who famously asked, "Where is everybody?" The numbers seem to be on the side of life. Our galaxy alone contains hundreds of billions of stars, and most of them are now believed to host planets. With so many worlds, it feels statistically inevitable that life would have arisen elsewhere, and that some of it would have evolved into intelligence capable of broadcasting its presence. So why the great silence? To grapple with this question, astronomer Frank Drake devised a now famous equation. The Drake equation is not a formula with a single answer, but a structured way to think about all the factors needed for a communicative civilization to arise. It multiplies variables like the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life actually emerges, the fraction where life becomes intelligent, the fraction that develops technology to communicate, and finally, the length of time such a civilization lasts. The challenge is that most of these values are still complete unknowns. This is where the search begins in earnest. Missions like NASA Kepler and TESS telescopes have revolutionized our understanding by discovering thousands of exoplanets. We now know that rocky worlds orbiting within their star's habitable zone, where temperatures could allow for liquid water, are common. The next step is to analyze the atmospheres of these distant worlds. Using powerful instruments like the James Webb Space Telescope, scientists look for biosignatures, chemical imbalances that could be produced by life. For example, the simultaneous presence of oxygen and methane in an atmosphere would be a strong, though not certain, indicator of biological activity. A recent, thrilling example was the detection of phosphine gas in the clouds of Venus. On Earth, phosphine is a gas produced almost exclusively by industrial processes or by anaerobic microbes. Its presence on our hostile neighbor sparked intense debate, a reminder that life, if it exists, might be found in the most unexpected places. This search extends to our own solar system. The barren surface of Mars may have hosted ancient microbial life, and robotic rovers are actively hunting for fossils or chemical traces. Icy moons like Jupiter's Europa and Saturn's Enceladus are prime targets, as they hide vast global oceans beneath their frozen crusts, warmed by the gravitational tug of their giant planets. Plumes of water vapor erupting from Enceladus offer a tantalizing opportunity to sample that hidden sea without even landing. Yet the silence persists, leading to the haunting Great Filter hypothesis. This idea suggests that there is at least one enormous, perhaps insurmountable, barrier that prevents life from progressing to the stage of interstellar colonization. The terrifying question is whether that filter is behind us or ahead of us. Did we somehow luckily pass a rare evolutionary step, like the emergence of complex cells, making us the first and only? Or is the filter still in our future, a destiny like self-annihilation through war or technology that awaits all advanced civilizations? Perhaps we are not listening correctly, or perhaps alien minds are so fundamentally different that their signals are unrecognizable to us. The search continues, a testament to our deepest hopes and our most profound fears, a quest that ultimately forces us to confront our own place in the silent, starry dark. That profound silence forces us to look inward, to the very origins of life on our own world. The leap from a sterile, rocky planet to a bustling biosphere is a mystery written in chemistry. How did inert molecules first organize themselves into something that could eat, grow, and replicate? The early Earth was a violent cauldron, bombarded by asteroids and crackling with lightning, yet within 1 billion years, life had taken hold. The scientific quest to understand this spontaneous generation, called abiogenesis, began in earnest with a landmark experiment in the 1950s. Chemists Stanley Miller and Harold Urey recreated the presumed atmosphere of the young Earth in a glass apparatus, a mix of water, methane, ammonia, and hydrogen. They passed electrical sparks through it to simulate lightning. After just a week, the once clear water had turned a murky pink and red. Analysis revealed that the experiment had produced a rich soup of organic molecules, including several amino acids, the fundamental building blocks of proteins. This was a revelation. It proved that the basic ingredients for life could form spontaneously from simple chemicals and energy. But making ingredients is one thing, building the chef is another. The next great challenge is the origin of genetics. How did a molecule emerge that could not only carry information but also copy itself? The leading hypothesis is known as the RNA world. RNA is a versatile molecule. It can store genetic information, much like its more famous cousin DNA, but it can also act as an enzyme catalyzing chemical reactions. Scientists like Jack Szostak have shown in the lab that under the right conditions, RNA strands can indeed replicate themselves, a crucial step toward Darwinian evolution. Perhaps the first life was not a cell at all, but a naked, self-replicating RNA molecule evolving in a tiny pool of water. But where on early Earth did these delicate processes find a safe haven? One compelling candidate is the deep-sea hydrothermal vent. These are not volcanoes of lava, but chimneys on the ocean floor that spew superheated, mineral-rich water into the cold, dark depths. They provide a constant source of energy and a rich gradient of chemicals, all sheltered from the violent surface world. The microscopic pores in the rock around these vents could have acted as the first cells, natural test tubes that concentrated the primordial soup and allowed the first metabolic reactions to occur. Another possibility looks to the stars. The theory of panspermia suggests that life's building blocks, or even dormant microbes, could have hitched a ride to Earth aboard comets and meteorites. We know that certain types of carbon-rich meteorites, called carbonaceous chondrites, are packed with amino acids and other organic compounds. In 1996, a meteorite designated LH8 4001 which was blasted off Mars and eventually landed in Antarctica, caused a global sensation. Scientists from NASA claim to see microscopic structures that resembled fossilized bacteria. The debate that followed was fierce, and most experts remained skeptical, but the very possibility highlights a thrilling idea. If life began independently on Mars, then it suggests the universe might be teeming with it. This brings us to the most difficult question of all: what exactly is life? We know it when we see it on Earth, but crafting a universal definition is notoriously tricky. Is it simply a self-sustaining chemical system capable of Darwinian evolution? If so, then the transition from chemistry to biology might not be a single, miraculous event, but a probable outcome wherever the right conditions persist for long enough. The search for answers now extends beyond our planet, to the dried riverbeds of Mars and the subsurface oceans of icy moons. Were we the result of a bizarre chemical accident on one world, or is life a fundamental, emergent property of a universe built to create? The answer will tell us if we are cosmic orphans or simply one branch on a vast galactic tree of life. The river of time feels like the most undeniable part of our reality, an unstoppable current carrying us from birth to death. Yet physics whispers a shocking secret. This flow, this relentless march from a fixed past into an open future, might be the grandest illusion of all. The equations that govern our universe, from Einstein's relativity to the core of quantum mechanics, are largely time-symmetric. They work just as well running backward as forward. This suggests a radical picture known as the block universe, where past, present, and future all exist simultaneously in a single, frozen, four-dimensional structure. We are simply conscious travelers crawling along our world line, mistaking our limited perspective for a universal flow. So why does time have such a definite direction? The answer appears to lie not in the fundamental laws, but in a single, powerful concept: entropy. The second law of thermodynamics states that the total disorder, or entropy, of an isolated system always increases over time. Think of a drop of ink falling into a glass of water. It starts ordered, a single dark droplet, and inevitably spreads into a uniform, disordered tint. You would never see the scattered ink particles spontaneously gather back into a single drop. This relentless increase in disorder gives us the arrow of time. It explains why we remember the past but not the future, why ice melts in a warm room, and why we grow old. The universe began in a state of incredibly low entropy at the Big Bang, a miraculously ordered starting point, and has been unraveling into higher states of disorder ever since. This cosmic one-way street is the source of time's apparent direction, but time is also stretchy. Einstein's theory of relativity tells us that time is not a universal metronome ticking at the same rate for everyone. It is a fluid dimension woven together with space, and it warps in the presence of matter and energy. The famous twin paradox illustrates this beautifully. If one twin rockets away on a spaceship traveling at near the speed of light and then returns, she will be younger than her Earth-bound sibling. Her high velocity literally slows down her passage of time relative to the stay-at-home twin. This is not a thought experiment. We prove it daily with the Global Positioning System, the atomic clocks on GPS satellites, orbiting high above Earth where gravity is slightly weaker, run measurably faster than identical clocks on the ground. Engineers must constantly correct for this relativistic effect, or your navigation would fail within minutes. Time itself flows at different rates on your head than it does on your feet. This strange, pliable nature of time leads to even more mind-bending possibilities. General relativity allows for theoretical constructs called closed time-like curves. paths through warped space-time that could, in principle, loop back on themselves, allowing travel into one's own past. While no such time machines are known to exist, their mathematical possibility within Einstein's equations is a profound hint that our understanding is incomplete. Some physicists, like Carlo Rovelli, propose that time is not fundamental at all, but an emergent property that arises from the quantum interactions of countless particles, much like temperature emerges from the jostling of atoms. If this is true, then at the most fundamental level, the universe might be timeless. The deep mystery of time is inextricably linked to the very first moment, to that singular state of infinite order from which our cosmic history began to flow. Streaking through the void are atomic bullets, the fastest moving matter we know of. These are cosmic rays, primarily the nuclei of atoms stripped of their electrons and accelerated to almost the speed of light. They are a constant, invisible rain upon our planet, and the most energetic among them carry more punch than the most powerful particle colliders ever built by humans. The record holder, detected over Utah in 1991, was so absurdly powerful it was nicknamed the "Oh my God" particle. This single subatomic particle, likely a proton, hit the atmosphere with the kinetic energy of a well-thrown baseball, all concentrated into a single fundamental speck. Where in the universe is there a cannon capable of such a feat? Detecting these ghostly bullets is a craft in itself. The most powerful cosmic rays are far too rare to catch with a small detector. Instead, we observe their spectacular death. When one slams into the top of our atmosphere, it creates a cascading avalanche of secondary particles, an extensive air shower that can spread over many square kilometers as it rains down upon the surface. Giant observatories like the Pierre Auger Observatory in Argentina use thousands of water tanks spread across 3,000 square kilometers to detect the faint flashes of light as these shower particles zip through them. By reconstructing the shower, we can trace the energy and direction of the original cosmic ray. The origin of these ultra-high energy particles is a profound puzzle. Their paths are scrambled by the magnetic fields that weave through interstellar and intergalactic space, bending and twisting their trajectories so we cannot simply look back to see where they came from. It is like trying to find the source of a wind in a hurricane, yet by mapping the arrival directions of the most energetic events, we see a faint, unsettling pattern. They do not seem to come from bright, nearby galaxies. Instead, they appear to originate from the vast, empty voids between galactic filaments, places where there is seemingly nothing at all. This points to sources that are incredibly distant and unbelievably violent. The prime suspects are the most energetic engines in the cosmos, active galactic nuclei, where supermassive black holes devour matter and blast out jets of plasma stretching for millions of light years, could act as natural particle accelerators. The shock waves from cataclysmic stellar explosions, gamma-ray bursts, might also be capable of this incredible feat. The leading theory for how they work is Fermi acceleration, where particles bounce back and forth across a magnetic shock wave, gaining a little more speed with each crossing until they are flung into the void at nearly light speed. But there is a limit. The universe is not completely empty. It is filled with the dim glow of the cosmic microwave background radiation. For a proton traveling from a distant galaxy, this background radiation is a wall of light. A proton with ultra-high energy will inevitably collide with these photons, creating new particles and sapping its energy. This theoretical ceiling is known as the Greisen-Zatsepin-Kuzmin, or GZK cutoff. The fact that we see particles with energies beyond this limit is a mystery in itself. Do they come from so nearby that they have not had time to be slowed? Or does their existence hint at physics beyond our standard model, perhaps from the decay of exotic, primordial particles left over from the Big Bang. Every time one of these cosmic bullets strikes our atmosphere, it is a message from the most extreme environments in the universe. They are intertwined with other cosmic messengers, like high-energy neutrinos and gamma rays, each telling a different part of the story. Unlocking their origin is not just about finding a celestial accelerator. It is about probing the fundamental laws of physics under conditions we can never hope to recreate on Earth. What unimaginable violence is required to launch a single particle across billions of light years with the force of a major league fastball? The answer is written in the faint flashes of light that grace our lonely planet. The universe has a speed limit, and we cannot agree on what it is. This is the heart of the Hubble Tension, a crack in the foundation of modern cosmology. It is a disagreement over how fast the cosmos is expanding, a number called the Hubble constant. The problem is stark. When we look at the ancient universe using the pristine snapshot of the cosmic microwave background from the Planck satellite, we get one very precise number for this expansion rate. But when we measure the modern, local universe using a cosmic distance ladder built from pulsating stars called Cepheid variables and brilliant stellar explosions known as Type 1, a supernova, we get a different, faster number. The two methods, one looking at the infant cosmos and the other at its recent adulthood, disagree significantly. It is like having two clocks in your house, one set by the atomic time standard and the other by the sunrise, and they stubbornly refuse to sync. This is not a small statistical fluke. The work of astronomers like Wendy Friedman and Adam Rees has refined the local measurements to such a degree that the discrepancy persists, suggesting it might be real. So what if our cosmic map is wrong? One thrilling possibility is that dark energy is not the constant force we thought. Perhaps it evolved over time, changing its strength in the early universe. This idea, called early dark energy, proposes a transient phase that would have subtly altered the conditions imprinted on the cosmic microwave background, making the early universe appear to be expanding at a slower rate than it truly was. This would reconcile the two measurements, but at a cost. It would mean our understanding of the universe's composition and evolution is fundamentally incomplete. We would have to introduce a new dynamic component to the cosmic recipe. Alternatively, the tension could be pointing to something even more exotic, like a new type of neutrino or an interaction between dark matter and dark energy that we have not yet accounted for. The implications ripple outward. A faster expansion rate would mean the universe is actually younger than we currently calculate. It would alter the timeline for the formation of the first galaxies and change our predictions for the ultimate fate of large-scale structures. This puzzle is deeply connected to the search for primordial gravitational waves, as certain patterns in the cosmic microwave background could rule out some of these exotic models. The Hubble tension forces a humbling realization. Our most precise measurements of the cosmos are now so good that they are revealing the limits of our own theories. We are not just arguing about numbers, we are grappling with the possibility that an unknown ingredient, a ghost in the cosmic machine, is subtly changing the expansion history of everything that exists. The majestic spirals and glowing ellipticals we see today were born from chaos. In the early universe, mere millions of years after the Big Bang, the cosmos entered a period known as the Dark Ages. There were no stars, no galaxies, only a pervasive fog of neutral hydrogen gas and the mysterious, invisible scaffolding of dark matter. Then something ignited. Within the densest knots of this dark matter web, trace amounts of normal gas began to cool, collapse, and fragment, lighting the first stars. These pioneers were not like our sun. They were behemoths, hundreds of times more massive, living fast and dying in colossal supernova explosions that seeded the void with the first heavy elements. This was the beginning of a billion-year construction project, the formation of the first galaxies. The leading blueprint for this cosmic assembly is the Lambda CDM model. Lambda stands for dark energy and CDM for cold dark matter. This theory posits a hierarchical, bottom-up structure. Small things merge to form bigger things. The gravitational pull of dark matter halos acted as traps, capturing vast reservoirs of gas. Within these halos, the first protogalaxies formed, and over time, they cannibalized their neighbors in a relentless dance of merger and acquisition. Our own Milky Way is a testament to this process, a giant that grew by consuming smaller dwarf galaxies, a history we can still read in the stellar streams orbiting our galactic halo. But the story is not just one of gravity. A crucial balancing force is feedback. When those first massive stars exploded, their supernova did two things. They blew enormous bubbles in the surrounding gas, ejecting it from the nascent galaxy and temporarily shutting down star formation. At the same time, they enriched that gas with carbon, oxygen, and iron, the very elements that would later form rocky planets and life. Later, supermassive black holes at the galactic centers joined the fray. When these monsters fed, they became active galactic nuclei, blasting out intense radiation and jets of plasma that could heat surrounding gas and regulate star formation across the entire galaxy. This intricate feedback loop, a battle between gravity's pull and explosive push, is what sculpts a galaxy's destiny, determining whether it becomes a ordered, star-forming spiral like Andromeda or a quiescent, red and dead elliptical. This process should have taken time, which is why the James Webb Space Telescope delivered such a profound shock. Peering back to the universe's infancy, it discovered galaxies that were already massive and mature, appearing far too soon after the Big Bang. They were fully formed when our theories said they should have just been beginning to assemble. This discovery has sent cosmologists back to the drawing board, questioning if the early universe was somehow more efficient at building galaxies, or if our understanding of the very first stars needs a radical revision. Why do galaxies look so different from one another? The beautiful diversity, from pinwheel spirals to featureless ellipticals, seems to be a product of their violent history. A spiral galaxy like our own likely enjoyed a relatively quiet life, with a steady inflow of gas allowing for continuous, ordered star formation. An elliptical galaxy, by contrast, is likely the product of a major merger, a cosmic car crash that violently scrambled orbits, used up the gas reservoir in a burst of star formation, and left behind a bloated, spherical remnant. Every galaxy we see is a fossil record of its unique past, a story written in the orbits of its stars and the composition of its gas. The mystery of their formation is inextricably linked to the dark matter halos they are embedded within and the vast cosmic web that connects them all. These invisible threads of force stretch for millions of light years, weaving through the emptiness between galaxies. Cosmic magnetic fields are the universe's silent puppeteers, guiding the paths of cosmic rays, shaping the birth of stars, and sculpting the evolution of entire galaxies. Yet, for all their influence, their origin is one of astronomy's most stubborn puzzles. How did these vast, organized fields emerge from the primordial, unmagnetized fire of the Big Bang? The challenge is that magnetic fields cannot simply appear from nothing. They require a seed, a tiny initial field, to be stretched and amplified. One of the leading mechanisms for creating this first spark is known as the Biermann battery effect. Imagine a cloud of hot, ionized gas, a plasma where the pressure and density are uneven. Electrons, being lighter, will drift away from ions in this turbulent soup. This separation of positive and negative charges creates a tiny electric current, and where you have electric currents, a magnetic field is born. It is a minuscule effect, but in the vast, churning cauldrons of the early universe, it could have provided the initial flicker. Once a seed field exists, the real cosmic dynamo kicks in. As plasma moves, especially when it is turbulent and rotating, it can stretch and twist these weak magnetic field lines, winding them up and transferring the energy of motion into magnetic energy. This is like twirling a button on a string, winding it tighter and tighter. Over hundreds of millions of years, this process, acting within galaxies and galaxy clusters, can amplify a seed field from a strength weaker than a common refrigerator magnet into the powerful, organized fields we observe today. We can see these fields indirectly. Radio telescopes are our primary tools, detecting the synchrotron radiation emitted by electrons spiraling at near light speed along magnetic field lines. They reveal intricate patterns, with fields often tracing the spiral arms of galaxies or forming vast, ordered structures in the colossal filaments of the cosmic web. These observations tell us the fields are real and powerful, but they do not tell us how the first seeds were planted. This leads to a profound frontier of cosmology. Could these seed fields be primordial, a relic imprinted directly by the processes of the very early universe? Some theories suggest that during cosmic inflation, that period of hyper-fast expansion, quantum fluctuations could have generated not only the seeds for galaxies but also the first magnetic fields. If this is true, then magnetism is as fundamental to the cosmos as matter itself, woven into the fabric of space-time from its first moments. Others look to more recent astrophysical violence. The shock waves from supernova explosions or the jets from active galactic nuclei could also generate seed fields through complex plasma processes. The truth may lie in a combination, a chorus of mechanisms working across cosmic time. The presence of these fields is not a minor detail. They are a fundamental part of the cosmic ecosystem. Within the Milky Way, our galaxy's magnetic field acts as a containment grid for the high-energy cosmic rays, forcing them to spiral and preventing them from simply streaming out into intergalactic space. In the dense, cold clouds where stars are born, magnetic fields provide a supporting pressure against the crushing force of gravity, regulating the rate at which stars can form and ultimately determining their size and number. Without magnetism, the cosmos would be a far different and perhaps far less structured place. Are we seeing the amplified echo of the Big Bang, or the cumulative product of stellar and galactic engines? The answer is written in the polarized light from the most distant quasars and the faint radio whispers from the early universe, a code we are only just beginning to crack. For a fleeting moment, it outshone the entire universe. In 2008, a gamma-ray burst occurred so powerful that for about 30 seconds, it was visible to the naked eye from Earth, despite having traveled 7.5 billion light-years. This event, known as GRB 080319b, was a staggering demonstration of raw cosmic power. Gamma-ray bursts are the most violent explosions since the Big Bang itself, and for a few precious seconds, they can release more energy than our Sun will over its entire 10 billion-year lifespan. These events come in two distinct flavors, each pointing to a different kind of cosmic cataclysm. The long bursts, lasting more than 2 seconds, are thought to be the birth cries of black holes. They occur when a massive star, dozens of times heavier than our Sun, exhausts its nuclear fuel. Its core collapses catastrophically, not into a neutron star but directly into a black hole. As it falls, the star's outer layers are ejected in two narrow, oppositely directed jets traveling at over 99.99% of the speed of light. Within these jets, internal shocks convert immense kinetic energy into a brilliant flash of gamma rays. We see the burst only if one of these deadly beams is pointed directly at Earth. The short bursts lasting less than 2 seconds are even more exotic. They are the death spirals of binary neutron stars. For millions of years, these two ultra-dense stellar corpses orbit each other, slowly losing energy by emitting gravitational waves. They inch closer and closer until, in a final millisecond, they slam together. The collision creates a black hole almost instantly, surrounded by a temporary, hyper-massless disk of leftover neutron star material. The resulting jets, blasting out from the poles of this newborn monster, produce the short, intense flash of a gamma-ray burst. Our understanding of this was revolutionized in 2017. The LIGO and Virgo observatories detected gravitational waves from a neutron star merger, event GW170817. Just 2 seconds later, the Fermi Gamma-Ray Space Telescope and the Integral Satellite observed a short gamma-ray burst from the exact same patch of sky. This was the dawn of multi-messenger astronomy, confirming the link between these mergers, gamma-ray bursts, and the creation of heavy elements like gold and platinum, which were forged in the neutron-rich debris ejected by the collision. The aftermath of a burst is just as important as the initial flash. Spacecraft like NASA's Swift satellite automatically swing into action when they detect a burst, rapidly pinpointing its location and observing the fading afterglow across X-ray, optical, and radio wavelengths. This afterglow is created when the jet plows into the surrounding interstellar material, creating an external shock that radiates for days or weeks. Studying this light tells us about the environment of the burst and the composition of the jet itself. Yet, profound mysteries remain. What is the exact engine that powers these relativistic jets? We know a newly formed black hole is involved, but the precise mechanism that draws in matter and focuses it into such narrow, powerful beams is still unknown. Some theories suggest intense magnetic fields are wound up like cosmic springs, while others point to the physics of the accretion disk itself. We also search for a third messenger, the neutrino. These ghostly particles could travel directly from the heart of the explosion, unaffected by magnetic fields, to tell us about the particle acceleration happening within. These bursts are not just spectacular fireworks, they serve as cosmic lighthouses because they are so brilliant we can see them from the very edge of the observable universe. Their light travels through billions of light years of intergalactic space, and by analyzing how that light is absorbed, we can take a census of the material between galaxies. They allow us to probe the history of star formation and the ionization state of the early universe. What extreme states of matter exist within these jets, where magnetic fields are trillions of times stronger than anything on Earth and temperatures are 1,000,000 times hotter than the Sun's core? Each burst is a fleeting message in a bottle, cast adrift from the most extreme physics in the cosmos. Billions of these cosmic phantoms pass through your body every second, leaving no trace. Neutrinos are the universe's most elusive particles, so reluctant to interact that most will travel through a light year of solid lead without a single collision. Their ghostly nature makes them nearly impossible to catch, yet they carry vital information from the most cataclysmic events in the cosmos. For decades, the standard model of particle physics assumed they were massless, but that comforting assumption was shattered by a profound discovery. Deep underground, in colossal detectors like Super Kamiok, and in Japan and the Sudbury Neutrino Observatory in Canada, physicists like Takoki Kajita and Arthur B. MacDonald found something astonishing. They proved that neutrinos oscillate, spontaneously changing their identity as they travel. an electron neutrino produced in the Sun can transform into a muon neutrino or a tau neutrino before it reaches Earth. This chameleon-like behavior has one Earth-shattering implication. Neutrinos must have mass. It was a discovery that earned them the Nobel Prize and forced a rewrite of the fundamental laws of physics. The amount of mass is almost vanishingly small. The tiniest neutrino is at least 10 million times lighter than an electron. But how do these phantoms acquire any mass at all? One compelling theory is the Seesaw Mechanism. It posits that alongside the familiar, lightweight neutrinos we know, there could exist incredibly heavy, sterile neutrino partners. The mass would be shared between them like two children on a seesaw. As one goes up in mass, the other goes down, explaining why our neutrinos are so inexplicably light. This opens a window into physics far beyond our current understanding. Their reluctance to interact makes them perfect cosmic messengers. When a massive star collapses in a supernova, the resulting blast of light can take hours to fight its way out of the stellar envelope. But neutrinos born in the core's furious collapse escape almost instantly. In 1987, detectors on Earth picked up a handful of neutrinos from a supernova in the Large Magellanic Cloud. They arrived hours before the visible light, offering humanity its first direct glimpse into the heart of a dying star. Today, we hunt for neutrinos from even more extreme sources. The Ice Cube Observatory, a cubic kilometer of pristine Antarctic ice instrumented with thousands of optical sensors, looks for the faint blue flashes created when a rare neutrino does collide with an atom. It has detected neutrinos from blazars, galaxies powered by supermassive black holes, tracing their origin back to these monstrous engines across billions of light years. But the greatest neutrino mystery of all concerns their very identity. Are neutrinos their own antiparticles? For most particles, like the electron, there is a distinct antimatter counterpart, the positron. But a theorized process called neutrinoless double beta decay would prove that the neutrino is its own antimatter twin. Experiments deep underground are searching for this incredibly rare decay. If found, it would not only revolutionize particle physics, but it could also solve one of the universe's most profound puzzles. Why is the cosmos made of matter and not antimatter? The Big Bang should have created equal amounts of both, leading to total annihilation. The fact that we exist means a fundamental asymmetry must have favored matter. If neutrinos are their own antiparticles, their unique properties could have tipped the primordial scales, allowing a universe of galaxies, stars, and ultimately, us to form. From the death of stars to the birth of the cosmos, these silent, whispering ghosts hold the keys to realities we are only beginning to perceive. The universe should have annihilated itself in a flash of light. In the first moments after the Big Bang, energy condensed into equal amounts of matter and antimatter. For every particle of matter created, a mirror image antiparticle was also born. When matter and antimatter meet, they destroy each other, leaving behind pure radiation. The entire cosmos should have been a brief, brilliant fire that swiftly faded to darkness. Yet here we are, in a universe filled with galaxies, stars, and planets, all made of matter. Something tipped the scales. This profound imbalance is known as baryogenesis, and it is one of the most urgent questions in all of physics. Why does anything exist at all? The brilliant physicist Andrei Sakharov outlined the three essential conditions needed for matter to gain an edge. First, there must be a process that violates baryon number conservation, meaning the total amount of matter in the universe is not fixed and can change. Second, the universe must depart from thermal equilibrium, creating a temporary, unstable state where the rules could be bent. And third, the interactions of particles must violate both charge conjugation symmetry, which swaps particles for antiparticles, and parity symmetry, which mirrors left and right. This combined breakdown is known as CP violation. We have actually observed CP violation in the laboratory. By studying the decays of strange particles called kaons and beauty mesons, physicists saw that matter and antimatter do not always behave as perfect mirror images. The decay rates are slightly different. It is a tiny effect, far too small to account for the overwhelming dominance of matter we see today, but it is a crucial clue that the symmetry can be broken. This search for asymmetry drives experiments at the Large Hadron Collider. Scientists recreate the seething quark-gluon plasma of the early universe, hoping to catch a glimpse of new particles or interactions that could have caused a much greater violation. One compelling theory is leptogenesis, which places the blame on the ghostly neutrino. In this scenario, heavy neutrinos in the early universe decayed asymmetrically, producing more matter than antimatter. This lepton asymmetry was then converted into a baryon asymmetry through subtle processes, filling the cosmos with the stuff we are made of. The evidence is written in the sky. The Planck satellite's map of the cosmic microwave background shows tiny fluctuations in temperature that are consistent with a universe that began with a 1 in a billion matter-antimatter asymmetry. Every structure we see grew from that initial, inexplicable surplus. We also search the heavens for any sign of antimatter galaxies, entire islands made of antistars and antiplanets. If such a place existed, the boundary where it met a matter galaxy would glow with the intense radiation of annihilation. So far, we have seen nothing. The cosmos appears to be made almost entirely of matter. This mystery ties directly into the Higgs boson, the particle that gives others mass. Could the Higgs field have undergone a phase transition in the early universe, a cosmic shift that permanently locked in the matter-antimatter imbalance? The answer lies at the frontier of our knowledge, in the subtle cracks between symmetry and the world we actually see. What fundamental process decided that existence would win over nothingness? That triumphant discovery in 2012 felt like the final piece of a cosmic puzzle. The Higgs boson, detected by the immense Large Hadron Collider, confirmed a theory first proposed by Peter Higgs, Francois Englert, and others nearly 5 decades earlier. It was a monumental achievement that completed the standard model of particle physics. Yet, in solving one great mystery, it unveiled even deeper and more unsettling questions about the fabric of reality. The Higgs boson is not just another particle. It is a ripple in an invisible cosmic molasses that fills all of space, the Higgs field. This field is what gives other fundamental particles their mass. Think of a celebrity trying to walk through a crowded room. They interact with the crowd, slowing down, acquiring a kind of social inertia. In the same way, particles that interact strongly with the Higgs field gain more mass, while those that barely interact, like photons, remain massless and zip through the universe at light speed. This elegant mechanism explains so much, but it also introduces a profound puzzle known as the hierarchy problem. The Higgs boson itself has a mass of about 125 billion electron volts. While that sounds immense, it is suspiciously light. According to our best theories, quantum fluctuations from the ultra-high energy realm of the Planck scale should drive the Higgs mass to a value 1,000,000 billion times larger. Why is it so comparatively small? It is as if a pencil balanced perfectly on its tip has remained upright for billions of years, defying the slightest breeze that should have knocked it over. This fine-tuning seems unnatural, pointing to the possible existence of new physics, like supersymmetry, which would introduce a shadowy partner for every known particle, whose quantum effects would neatly cancel out these destabilizing fluctuations and explain the Higgs lightness. But so far, the Large Hadron Collider has found no evidence for these superpartners. This leads to a truly cosmic concern, the stability of the vacuum itself. The shape of the Higgs field's potential energy might not be a simple, stable valley. Our universe might exist in a false vacuum, a metastable state like a ball resting in a small dip on the side of a much steeper hill. A powerful enough jolt, perhaps from a cosmic collision, could theoretically knock the Higgs field out of its current state, triggering a bubble of true vacuum that expands at the speed of light. This event, known as vacuum decay, would rewrite the laws of physics in its wake, dissolving atoms and ending the universe as we know it. Fortunately, calculations suggest our vacuum is likely stable for many billions of years, but the mere possibility highlights the precariousness of our cosmic situation. Physicists are now meticulously measuring how the Higgs boson interacts with other particles, its couplings, searching for any tiny deviation from the standard model's predictions. Such a deviation would be a crack in the foundation, a signpost to something greater. They also hunt for additional, heavier Higgs bosons, which are predicted by many theories that extend beyond our current understanding. The Higgs field's role in the early universe is equally dramatic. In the first moments after the Big Bang, as the cosmos cooled, the Higgs field likely underwent a phase transition, settling into its current value and giving mass to the universe. But what if it had tilted differently? A slightly different value could have resulted in electrons with too much mass, preventing chemistry, or atoms that could not form. Our universe is a product of this specific Higgs setting. This intimate connection between the tiniest particles and the grandest cosmic scales is breathtaking. Does the peculiar nature of the Higgs point toward a vast multiverse, where every possible value is realized in a separate bubble universe, or could its properties be a hint of hidden, compactified dimensions? The Higgs boson is not an end. It is a gateway, a bridge from the world we know to a far stranger and more magnificent reality waiting to be discovered. A sudden flash of radio light from a distant galaxy can outshine an entire sun for a few fleeting milliseconds. These are fast radio bursts, cosmic enigmas first discovered in 2007, whose true nature remains one of the most urgent puzzles in modern astronomy. In that blink of an eye, a single burst can release more energy than our sun emits in 80 years, a staggering output for such a transient event. The first major clue came with FRB 121102, a burst that did something extraordinary. It repeated. This was not a one-time cataclysm, but a source that could fire again and again, ruling out any model that required the total destruction of the object. This repeater was traced back to a small, turbulent dwarf galaxy, a place buzzing with active star formation. The localization was a triumph, made possible by powerful radio telescope arrays like CHIME in Canada and ASCAP in Australia, which can scan vast swaths of the sky to catch these unpredictable flashes. How do we even know how far away they are? The key is in the signal itself. As the radio waves travel across millions of light-years of intergalactic space, they encounter free electrons. Higher frequency waves travel slightly faster than lower ones, causing the burst to disperse, to spread out in time. By measuring this dispersion, this smear in the signal, astronomers can estimate the total amount of material the burst has passed through, and therefore its distance. The leading suspect for at least some of these bursts is a magnetar, a type of neutron star with an almost unimaginably powerful magnetic field. Picture a magnetic field so intense that it could erase a credit card from halfway to the moon. A starquake on the surface of such a monster, a sudden cracking of its rigid crust, could unleash a titanic shockwave, powering a brilliant, coherent radio blast. Other potential culprits include the mergers of neutron stars, the same events that produce short gamma-ray bursts, or even the theoretical evaporation of primordial black holes. The diversity of the bursts is bewildering. Some are one-off events, perhaps the final death cry of a unique stellar process. Others, like the famous repeater, suggest a source that can survive its own violent outbursts. Could there be a connection to active supermassive black holes, with their chaotic environments providing the perfect particle accelerator? Or, in a more speculative vein, could these be signs of advanced alien technology, like powerful interstellar beacons or light sails? While natural explanations are overwhelmingly favored, the sheer power and brevity of the signals force us to consider all possibilities. Beyond their mysterious origins, fast radio bursts have become unexpected tools for cosmic cartography. Each burst is a messenger that has traveled through the lonely voids between galaxies. By analyzing how the signal has been stretched and scattered, we can measure the density of this missing matter, mapping the invisible web that constitutes the large-scale structure of our universe. They illuminate the cosmic highways that light alone cannot reveal. What physical mechanism can possibly concentrate such phenomenal energy into a pulse shorter than a human heartbeat? The answer may lie in a new type of astrophysical engine, one that operates under laws of physics we have yet to fully comprehend. Every millisecond flash is a challenge, a reminder that the universe is still capable of surprising us with its raw, untamed power. A star's death is one of the universe's most spectacular finales. For a star like our Sun, the end is relatively peaceful, a slow fading into a white dwarf. But for a star more than 8 times the mass of our Sun, the finale is a cataclysm of almost unimaginable violence, a core collapse supernova. This process forges the very elements that make up our world and seeds the cosmos with the remnants that will become new stars, planets, and perhaps even life. The story begins deep within the star's core, which has been acting as a nuclear furnace for millions of years, fusing hydrogen into helium, and then helium into heavier elements like carbon and oxygen. This fusion process is a constant battle against the star's own immense gravity. When the core finally fuses its way to iron, the battle is lost. Iron is nuclear ash. Fusing iron does not release energy, it consumes it. With its energy source cut off, the core has no defense against gravity's crushing pull. In less than a second, a core that was once the size of Earth collapses into a sphere just a few dozen kilometers across, a density so extreme that protons and electrons are forced together to form neutrons. This new neutron core is so rigid it halts the collapse, and the infalling outer layers of the star rebound off this impossibly hard surface, creating a shock wave that races outward, blasting the entire star apart. This is the supernova explosion, briefly outshining its entire host galaxy. Yet, for decades, computer simulations of this process had a frustrating problem. The shockwave would stall. It simply did not seem to have enough energy to successfully blow the star apart. The missing ingredient, we now believe, is the ghostly neutrino. During the core collapse, an immense flood of neutrinos is generated, carrying away 99% of the star's gravitational energy. A small fraction of these neutrinos, just 1 or 2%, can deposit their energy behind the stalled shockwave, reheating it and powering the explosion like a cosmic engine starter. This delicate interplay of neutrinos and hydrodynamic instabilities is the heart of the supernova problem, a puzzle that requires immensely complex, multi-dimensional simulations to solve. The fate of the collapsed core depends entirely on its final mass. This is defined by critical limits discovered by brilliant astrophysicists. The Chandrasekhar limit, about 1.4 times the mass of our Sun, is the maximum mass a white dwarf can support against its own gravity. For neutron stars, the Oppenheimer-Volkoff limit, around 2 or 3 solar masses, marks the boundary between a stable neutron star and a total collapse into a black hole. What remains after the explosion is a compact object of incredible density. A neutron star is a city-sized sphere where a teaspoon of material would weigh billions of tons. Some neutron stars, known as pulsars, are cosmic lighthouses. Discovered by Jocelyn Bell Burnell in 1967, these objects beam radiation from their magnetic poles, and as they rotate, we see a regular pulse of light if the beam sweeps past Earth. The Crab pulsar, at the heart of the Crab Nebula, the remnant of a supernova observed in 1054, spins 30 times every second. The study of these objects pushes the limits of physics, probing the equation of state for nuclear matter, which describes how matter behaves under such extreme pressure. Are neutrons packed together like a fluid, or do they retain some substructure? When two neutron stars spiral together and merge, as detected by LIGO in 2017, they create ripples in space-time and forge heavy elements like gold and platinum, scattering them across the cosmos. If the collapsing core is too heavy, no force in the universe can stop its complete and total collapse into a black hole, a gravitational abyss from which not even light can escape. The death of a star is not an end but a transformation, a violent and creative act that echoes across the galaxy, leaving behind the seeds for future worlds and the most exotic objects in the universe. Our galaxy is not drifting aimlessly through the cosmos. The Milky Way, along with our entire local group of galaxies, is racing through space at a staggering 2 million kilometers per hour, pulled by a hidden source of immense gravity. This motion is not just the general expansion of the universe. It is a specific, anomalous flow toward a mysterious region in the constellation Centaurus, a place astronomers call the Great Attractor. The problem is we cannot see it directly. Our view from within the Milky Way's disk is blocked by the thick dust and stars of our own galaxy's bulge, a zone astronomers poetically call the zone of avoidance. It is the ultimate cosmic irony to be pulled toward something we are fundamentally blind to. For a long time, the nature of this gravitational phantom was one of astronomy's most frustrating puzzles. How do you map an invisible monster? The key was to stop looking with visible light and instead listen to the sky in other wavelengths. Large-scale surveys like the 2-micron All-Sky Survey, or 2MISS, used infrared telescopes to peer through the galactic dust, revealing thousands of previously hidden galaxies. Meanwhile, the HI-PARCS All-Sky Survey, or HIPSS, mapped the distribution of neutral hydrogen gas using radio waves, another way to see through the obscuration. These projects began to outline the true source of the pull. It is not a single, impossibly dense object, but a vast gravitational watershed, a continent of galaxies known as the Laniakea supercluster. Our Milky Way is just a small town on the outskirts of this immense structure, which contains over 100,000 galaxies. The Great Attractor is the gravitational center of this supercluster, enormous concentration of mass where the flow of galaxies converges. But what provides the gravity? The visible galaxies we can now see are not nearly enough to account for the tremendous pull. The real engine is the dark matter halo in which this entire structure is embedded. This invisible scaffold amplifies the gravity of the visible matter, creating a deep enough gravitational well to dictate the motion of our entire galactic neighborhood. The estimated total mass of this region is a mind-numbing 10 quadrillion times the mass of our Sun. Yet the story grows even more complex. Our motion is not solely due to the Great Attractor. Further observations suggest we are also being pulled toward an even larger and more distant concentration of mass, the Shapley supercluster, the most massive known structure in our local universe. It lies hundreds of millions of light-years beyond the Great Attractor, and its collective gravity adds to our cosmic river flow, so we are caught in a cosmic tug-of-war between these two massive overdensities. This grand picture of flowing galaxies, mapped through painstaking observations, provides some of the most compelling evidence for the large-scale structure of the cosmos, a web of dark matter and galaxies stretching across billions of light-years. Is the Great Attractor a unique anomaly, or is every supercluster centered on such a gravitational anchor? The answer lies in the distribution of the unseen, the dark matter that truly guides the grand motions of the universe, pulling us toward a destiny we are only beginning to perceive. Two particles born together can remain linked in a ghostly embrace, no matter how far apart they fly. This is quantum entanglement, a phenomenon so strange that Albert Einstein himself called it spooky action at a distance. When you measure a property of one entangled particle, like its spin, its partner instantaneously snaps into the corresponding state, seemingly communicating faster than light. Yet, this is not a mechanism for sending messages. It is a deeper connection that hints at a profound oneness in the fabric of reality. For decades, this was a philosophical curiosity, but physicist John Stuart Bell devised a mathematical theorem that could test it. Experiments have since confirmed that entanglement is real, with photons remaining linked over distances of hundreds of kilometers. This bizarre connection is not just a laboratory trick. It may be the secret ingredient that holds the universe together. The holographic principle suggests that all the information describing a three-dimensional volume of space, like the interior of a black hole, is perfectly encoded on its two-dimensional boundary. What is the glue that makes this encoding possible? The answer appears to be quantum entanglement. The threads that stitch together the fabric of space-time itself might be woven from these spooky correlations. This leads to one of the most stunning ideas in theoretical physics, the ER=EPR conjecture. It proposes that two entangled particles are, in fact, connected by a microscopic wormhole, a bridge through the geometry of space-time. What we perceive as spooky action across a distance might actually be a direct physical connection through a hidden dimension. This idea provides a potential solution to the black hole firewall paradox. If entanglement is what creates the geometry of space, then the event horizon might not be a blazing wall of fire after all, but a complex web of quantum connections. The entropy of a black hole, a measure of its information content, is proportional to its surface area, not its volume. This Bekenstein-Hawking area law finds a natural explanation if the entropy arises from the entanglement between the inside of the black hole and the radiation leaking out. The implications stretch all the way back to the Big Bang. Could the rapid expansion of cosmic inflation have been powered by a vast network of entanglement, stitching the newborn universe into a coherent whole? Today, we are harnessing this phenomenon to build quantum computers, which use entangled qubits to perform calculations impossible for classical machines. The same spooky action that Einstein questioned might one day unlock new technologies and reveal that the cosmos is not a collection of separate objects, but a single, deeply interconnected quantum system. Is our perception of empty space an illusion, emerging from an unimaginably dense tapestry of quantum links? The moon's surface holds frozen treasure hidden in eternal darkness. For centuries, we thought our celestial neighbor was a completely barren world, but we were wrong. Deep within polar craters like Shackleton, places where sunlight has not shone for billions of years, water ice survives in the profound cold. This discovery forces a fundamental question: where did the moon's water come from? The answer rewrites the history of our entire cosmic neighborhood. The leading theory for the Moon's very existence is the giant impact hypothesis. Billions of years ago, a Mars-sized object named Theia is thought to have slammed into the young Earth. The cataclysmic collision vaporized rock and metal, blasting a tormented ring of debris into orbit that eventually coalesced into the Moon. This violent birth in a furnace of heat should have boiled away any volatile substances like water. So how did it return? One possibility is that it arrived later, delivered by a steady rain of icy comets and water-rich asteroids during the early solar system's chaotic period of heavy bombardment. These cosmic ice cubes crashed into the lunar surface, and some of their water found its way into the permanent shadows of the polar craters, creating a natural deep freeze. Another source is the Sun itself. The solar wind is a constant stream of charged particles, including hydrogen ions, blowing from the Sun. When these hydrogen ions hit the lunar soil or regolith, they can chemically react with oxygen-bearing minerals to create water molecules right on the surface. This process is a slow, steady drizzle of creation. A third, more intriguing idea is that the Moon itself outgassed water from its interior. Perhaps the giant impact did not completely dehydrate the Moon, and pockets of water survived deep underground, later seeping to the surface through volcanic activity. The evidence for water is now undeniable. In 2009, NASA LCROSS mission deliberately slammed a rocket stage into the permanently shadowed Cabeus crater. The following spacecraft flew through the resulting plume, analyzing its composition before it too impacted. The data was clear. The plume contained a significant amount of water vapor and ice crystals. India's Chandrayaan-1 orbiter also played a pivotal role, using its Moon mineralogy mapper to detect the chemical signature of water molecules bound to the soil across large swaths of the lunar surface. This points to a dynamic, if subtle, water cycle. Water molecules formed on the sunlit areas can hop across the surface, propelled by the faint heat of sunlight, until they migrate into a cold trap, a shadowed crater where they freeze and remain stable for eons. The regolith itself acts as a sponge, its porous structure helping to trap and preserve these precious icy deposits. This is not just a scientific curiosity. It is the key to humanity's future in space. Water is the oil of solar system exploration. It is not just for drinking. When split into its components, hydrogen and oxygen become rocket fuel and breathable air. A lunar base with access to this local resource could become a permanent outpost and a fueling station for voyages deeper into the solar system. The Moon becomes a cosmic gas station. The water locked in lunar ice also tells a story about our own planet. Did Earth receive its oceans from the same cometary and asteroidal delivery service? Studying the isotopic fingerprints of lunar water and comparing it to Earth's could reveal if we share a common source. This mystery connects our Moon to other icy worlds, like Jupiter's moon Europa, which hides a global ocean under its crust. How water, the essence of life, is distributed and preserved across the cosmos is a central theme of planetary science. The silent, shadowed craters of the Moon hold a record of the solar system's early history, a frozen archive waiting to be read. A distant world glows against the blackness of space, its atmosphere a thin, brilliant halo as it transits its star. We are no longer just finding exoplanets, we are beginning to taste their air. The 25th Great Mystery asks what is the true nature of these alien skies. With the James Webb Space Telescope, we have a new tool to dissect this light, using a technique called transmission spectroscopy. As a planet crosses in front of its host star, a tiny fraction of the starlight filters through its atmosphere. Different gases in that alien air absorb specific colors of light, leaving behind a unique chemical fingerprint. By reading this barcode, we can identify molecules like water vapor, methane, and carbon dioxide from hundreds of light years away. Pioneers like Sarah Seeger and the late David Charbonneau developed these methods, turning distant points of light into worlds with weather and composition. The ultimate goal is to find a biosignature, a gas or combination of gases that strongly suggests the presence of life. On Earth, the simultaneous presence of oxygen and methane is a powerful sign, as these gases react quickly and destroy each other. Their continuous existence requires a constant source like biology to replenish them, but the interpretation is fraught with challenge. The type of star matters immensely. A quiet, stable star like our Sun is ideal, but many planets orbit volatile red dwarfs, which frequently erupt with flares that can strip away an atmosphere entirely. The planet's distance from its star defines its habitable zone, the region where temperatures could allow for liquid water. Yet, even within this zone, a planet's atmosphere is its life support system, a shield and a climate regulator. Thick clouds and high-altitude hazes can obscure our view, hiding the telltale signs of molecules below and complicating our models of these alien environments. Some of the first atmospheres we characterized belonged to hot Jupiters, gas giants orbiting perilously close to their stars. These worlds are laboratories of extreme chemistry, with temperatures so high that rocks vaporize and condense into clouds of molten silicate, raining liquid gemstones. They showed us that planetary atmospheres can be far more exotic than anything in our own solar system. Then there is the TRAPPIST-1 system, a compact family of 7 rocky planets orbiting a cool red dwarf. Several of these worlds sit in the habitable zone, and the James Webb Space Telescope is now probing their atmospheres, searching for the signs of water or carbon dioxide that would mark them as true candidates for Earth-like conditions. The search is not without surprises, as the fierce debate over phosphine on Venus reminded us. Its tentative detection, a gas often linked to biological activity on Earth, forced a global re-examination of the complex chemistry of our sister planet. It was a stark lesson that a potential biosignature must be scrutinized from every angle, as geological or photochemical processes we do not yet understand could be the true culprit. This work forces us to ask what gases would be a definitive sign of life and how long a planet can cling to its protective blanket of air. Mars stands as a solemn example, a world that lost its thick atmosphere to the solar wind, transforming from a warm, wet planet into a frozen desert. The study of exoplanet atmospheres is not just about chemistry, it is about the stability of worlds and the delicate conditions that allow life to arise and persist. Each new spectrum is a message in a bottle, a clue to whether we are alone in a silent cosmos or simply one voice in a cosmic chorus. A swirling disk of gas and dust, a cosmic nursery around a newborn star, holds the blueprint for entire worlds. This is the genesis of a planetary system, a process we are only beginning to decipher in all its chaotic beauty. The primary theory for how planets are born is called core accretion. It starts with microscopic dust grains within the protoplanetary disk colliding and sticking together, slowly building up into larger and larger bodies, from pebbles to planetesimals, and finally to planetary embryos. For rocky worlds like Earth, this is a relatively local process, but for gas giants like Jupiter, the story is more dramatic. A massive planetary core, perhaps 10 times the mass of Earth, must form quickly enough to gravitationally capture the vast envelope of hydrogen and helium gas before the young star's radiation blows it all away. This race against time explains why gas giants are typically found farther from their host stars, where the disk is colder and material is more plentiful. An alternative, more rapid path is gravitational instability. Here, a massive cold disk of gas and dust could spontaneously fragment under its own gravity, directly collapsing into giant planets. This might explain the existence of planets on incredibly wide orbits, like those in the HR 8799 system, where 4 giant worlds have been directly imaged at distances far greater than Neptune's from our Sun. Our window into this cosmic construction zone has been blown open by the Atacama Large Millimeter Array, or ALMA. This powerful radio telescope has captured stunning, high-resolution images of protoplanetary disks, revealing intricate structures of bright rings and dark gaps. These gaps are likely being carved out by infant planets as they sweep through the disk, clearing their orbital paths and gathering material. But the journey of a young planet is not a stationary one. Through interactions with a gaseous disk, planets can migrate inward or outward. A planet's gravity creates spiral density waves in the disk, and the gravitational pull from these waves can cause the planet to lose orbital energy, drifting steadily closer to the star. This process of planetary migration could explain the existence of hot Jupiters, gas giants orbiting perilously close to their stars, which surely could not have formed in such infernal regions. This dynamic movement also leads to a phenomenon known as orbital resonance, where the orbital periods of planets form a precise ratio. In our own solar system, Jupiter's moons are a classic example, but this occurs with planets too. It is a fossil record of their early migration, a gravitational synchrony locked in place as they drifted through the primordial disk. The formation of a planetary system is a delicate dance, easily disrupted. In binary star systems, the gravitational tug from a companion star can truncate the protoplanetary disk, limiting the amount of material available and potentially throwing planet formation into chaos. And throughout this entire process, the young star itself is an active participant, blasting out powerful winds and radiation that can strip away the atmospheres of inner planets or evaporate the entire disk over millions of years. The final act involves the delivery of life's ingredients. Water, essential for life as we know it, is thought to have been delivered to early Earth by water-rich asteroids and comets from the outer solar system, a late cosmic rain that filled our oceans. This grand narrative, from dust to diverse worlds, raises a profound question. Is our own solar system, with its orderly arrangement of rocky inner planets and gaseous outer giants, a common outcome, or is every planetary system a unique and unpredictable work of art? The answer lies in the faint, swirling glow around infant stars, where the next generation of Earths and Jupiters are taking shape. Beyond the last known planets lies a frozen frontier, a vast disk of icy remnants known as the Kuiper Belt. This is not empty space, but a sprawling junkyard of primordial material, a cosmic deep freeze preserving the building blocks of the solar system's outer reaches. Dwarf planets like Pluto, Haumea, and Makemake are not misfits, but kings of this distant realm, the largest known members of a countless population of icy bodies. Their very existence tells a story of a construction project that was never finished, where the planetesimals of the outer solar system never coalesced into another giant world, likely due to the gravitational influence of Neptune. The architecture of this belt is defined by this relationship with the ice giant. Many objects, including Pluto itself, are locked in an orbital resonance with Neptune. This means that for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This gravitational synchrony keeps their paths stable, preventing a catastrophic collision or ejection. Objects in this 2 to 3 resonance are called plutinos, while other bodies, known as cubanos, orbit farther out in more circular paths, relatively free from Neptune's direct sway. The dynamic history of this region is chaotic. the leading theory, known as the Nice model, suggests the giant planets did not form in their current positions. In a grand planetary migration, Jupiter, Saturn, Uranus, and Neptune shifted orbits, their gravitational wake scattering countless icy bodies inward and outward. This cosmic shuffle likely placed Neptune at the outer edge of the planetary disk, where it now shepherds the Kuiper belt, its gravity sculpting the orbits of everything within its reach. But some orbits defy even this explanation. The seductive mystery of a massive, unseen planet emerges from the peculiar paths of a handful of extreme trans-Neptunian objects. Sedna, for instance, follows a long, lonely ellipse that takes it thousands of times farther from the Sun than Earth, yet it never comes close enough to be influenced by the known giants. Its orbit and those of a few others appear strangely clustered, as if they are all being shepherded by the same invisible hand. This is the core of the Planet 9 hypothesis, championed by astronomers like Mike Brown and Konstantin Batygin. They propose a world with perhaps 10 times the mass of Earth, lurking in the darkness on an immensely long orbit, its subtle gravitational tugs orchestrating these distant dances from hundreds of astronomical units away. The search for this phantom world is one of modern astronomy's great quests. Our first close-up look into this realm came from NASA's New Horizons mission. After its breathtaking flyby of Pluto in 2015, revealing a complex world of mountains of water ice and vast nitrogen glaciers, the spacecraft continued onward to a small, bilobed object named Arrokoth. Resembling a cosmic snowman, Arrokoth is a pristine contact binary, two ancient planetesimals that gently merged in the solar system's infancy. Its smooth, unblemished surface and remarkable red color suggest it has been in a deep freeze for over 4 billion years, a perfectly preserved fossil from the dawn of planetary formation. This tells us the Kuiper belt is a repository of the original material from which the planets were made, a time capsule of incredible value. Every new object discovered, from the dwarf planet Eris that famously challenged Pluto's planethood to the bizarre, rapidly spinning Haumea with its ring system, adds another piece to the puzzle. The Kuiper belt is the gateway to an even more distant and mysterious region, the Oort cloud, a spherical shell of icy bodies believed to be the source of long-period comets. What other frozen worlds, or perhaps even a hidden giant, are waiting to be found in the perpetual twilight beyond Neptune? Far beyond the last icy wanderers of the Kuiper belt lies a realm of pure theory, a ghostly halo of frozen worlds that marks the final gravitational outpost of our Sun. This is the Oort cloud, a vast, spherical shell of trillions of icy objects enveloping our entire solar system. We have never seen it directly, for its nearest members are still unimaginably distant, but we know it must be there because of the long-period comets that fall from the depths of space. These comets, like the magnificent Hale-Bopp which graced our skies for 18 months, arrive on immense, looping orbits that can take thousands or even millions of years to complete. They come from all directions, not just from the flat plane of the planets, which points to a spherical reservoir of icy bodies, a concept first proposed by the Dutch astronomer Jan Oort. How did this cosmic deep freeze form? The story begins in the violent youth of our solar system. As the giant planets Jupiter, Saturn, Uranus, and Neptune settled into their orbits, their immense gravity acted like a cosmic slingshot, flinging countless leftover planetesimals, the building blocks of planets, out into the void. Some were ejected entirely, becoming rogue objects drifting between the stars. Others were thrown just far enough to reach a gravitational balance, settling into this distant cloud, their orbits stretched and randomized by the gentle but persistent tug of the Milky Way itself. Galactic tides, the subtle pull from the mass of our galaxy's disk, and occasional close encounters with passing stars, nudge and perturb these frozen relics, occasionally sending one on a fatal dive toward the inner solar system, where the sun's warmth transforms it into the blazing spectacle of a comet. This cloud is thought to contain more than 1 trillion individual objects, a staggering number, yet they are so spread out across such a colossal volume that they are effectively invisible to our telescopes. The inner edge of this cloud may begin about 2,000 astronomical units from the Sun, but its outer boundary could extend a light year or more, halfway to the next star. This immense distance is the primary reason we cannot observe it, placing these objects far beyond the reach of even our most powerful instruments. The existence of the Oort cloud provides a compelling context for interstellar interlopers like Oumuamua, the strange, elongated object that sped through our solar system. It is possible that every star is surrounded by its own similar cloud of icy debris, and that these objects are constantly being exchanged between stellar systems, a gentle trade in frozen fossils from one cosmic neighborhood to another. The study of this theoretical cloud is ultimately a study of our solar system's final frontier and its relationship with the wider galaxy. It is a frozen archive of our own origins, holding pristine material from the very beginning, and its dynamic interplay with the Milky Way reminds us that our solar system is not an isolated island, but a participant in the grand gravitational dance of the cosmos. What other secrets are locked in that deep freeze, waiting for a stellar nudge to send them falling toward the light? The smooth fabric of space-time described by Einstein might be an illusion, a mere average of a far wilder reality. At the very smallest scales, at a size known as the Planck length, the quiet geometry of the cosmos is theorized to boil and churn. This is the concept of space-time foam, a turbulent, frothy sea born from relentless quantum fluctuations, where tiny wormholes might blink in and out of existence, and the very concepts of before and after lose their meaning. The physicist John Wheeler, who coined the term, envisioned a reality where at this fundamental level, the topology of space-time itself is constantly changing, like the bubbly, effervescent surface of a freshly poured glass of champagne. To grasp the scale, a single Planck length is so inconceivably small that if you enlarged an atom to the size of our observable universe, a Planck length would be roughly the height of a single tree. It is here, in this realm of the almost infinitely tiny, that the smooth continuum of general relativity must finally surrender to the chaotic rules of quantum mechanics. How do we possibly describe such a thing? Two leading theories offer radically different pictures. Loop quantum gravity proposes that space is not smooth, but woven from a fabric of tiny, finite loops, a spin network. In this view, space is quantized, composed of discrete, indivisible units, much like a digital photograph is made of individual pixels. The foam, then, is the dynamic, vibrating network of these fundamental threads. String theory, on the other hand, suggests that the foam arises from the complex interactions and vibrations of the universe's most basic constituents, tiny strings, playing out in a reality with many more hidden dimensions. This leads to one of the most profound ideas in modern physics, the holographic principle. It proposes that all the information needed to describe a three-dimensional volume of space can be perfectly encoded on its two-dimensional boundary, just as a three-dimensional image is encoded on a flat, two-dimensional hologram. In this astonishing view, the frothy, complex interior of our universe might be a projection from a vast, entangled quantum system living on its outer edge. The foam is not just a theoretical curiosity, it could have observable consequences. If space-time is grainy, then two photons of different energies traveling across billions of light-years from a distant gamma-ray burst would not arrive at exactly the same time. The higher energy photon, interacting more with the frothy texture of space, might be slowed by a minuscule amount. By analyzing the arrival times of these photons, astronomers are, in effect, using the universe as a colossal microscope to probe the structure of space-time itself. So far, no such blurring or delay has been conclusively found, placing stringent limits on the foam's possible graininess. This search pushes the boundaries of what is testable, connecting the furious energy of stellar explosions to the quiet hum of the quantum vacuum. If space-time is discrete, what does that mean for the nature of singularities at the hearts of black holes? Could their infinite density be replaced by a dense, foamy structure governed by quantum geometry? The answer would redefine our understanding of existence, suggesting that the stage upon which the cosmic drama plays out is not a passive backdrop, but a dynamic, participatory entity, forever churning beneath the surface of our perception. A tiny, persistent push was holding the Pioneer spacecraft back. As Pioneer 10 and 11 journeyed beyond the planets, navigators noticed a bizarre and constant sunward deceleration, a force so slight it was barely measurable, yet it defied all expectations. This was the Pioneer Anomaly, a ghost in the machine that for decades fueled speculation about a crack in our understanding of gravity itself. The data, meticulously analyzed by scientists like John Anderson, revealed an acceleration towards the Sun that was just a 10/1000th of the gravity we feel on Earth. It was a whisper from the void, a hint that perhaps Newton's or even Einstein's laws needed revision in the deep, quiet reaches of the solar system. Could this be evidence for modified Newtonian dynamics, or MUND, a theory proposing that gravity behaves differently at very low accelerations? For a time, it seemed like a portal to new physics. The true answer, however, proved to be far more mundane, yet no less brilliant in its detective work. A team led by Slava Turyshev dove into the problem, recovering decades-old telemetry data and building a complex thermal model of the aging probes. The culprit was not gravity, but heat. The spacecraft's radioactive power generators produced heat, which was then radiated away from the vessels. The key was that this radiation was not perfectly symmetrical. A tiny, anisotropic push from the warmth emitted by the spacecraft's own systems was acting as a gentle brake, providing just enough force to account for the anomalous deceleration. This explanation was a triumph of engineering over exotic physics, but it did not completely close the case. Precise modeling of this thermal recoil force remains incredibly difficult, and some residual uncertainty lingers at the very edge of the error bars. Could there still be a minuscule, unaccounted-for gravitational effect at play? The legacy of the Pioneer Anomaly is a lesson in humility. It taught us to exhaust every conceivable mundane explanation before invoking new laws of nature. It forced a new level of rigor in deep space navigation, influencing the design of missions like New Horizons, which, traveling faster and on a different trajectory, has shown no such anomaly. This cosmic detective story reminds us that the universe's greatest secrets are sometimes hidden not in distant galaxies, but in the subtle, overlooked details of our own celestial backyard. What other whispers are we missing in the vast, quiet expanse, masked by the hum of our own technology? These mysteries are not isolated puzzles but threads in a single, grand tapestry. Each unsolved question pushes against the limits of our technology, forcing us to build more sensitive ears and sharper eyes to listen to the cosmos. The hunt for dark matter, for instance, is driving the creation of ever more secluded laboratories, buried deep beneath mountains to shield them from cosmic noise. where scientists wait for the almost impossible click of a phantom particle. Our struggle to understand the universe's accelerating expansion fuels the launch of space telescopes that act as cosmic clocks, measuring the stretching of space with breathtaking precision. This technological march is not just for answers, it is a fundamental expression of human curiosity, a bridge between the abstract mathematics of theoretical physics and the tangible reality of a machine we send to another world. The questions that keep us awake at night are the very ones that get us out of bed to build something new. The next generation of observatories will peer into realms we have only dreamed of. The Square Kilometre Array, a vast network of radio antennas, will listen for the faint whispers of hydrogen from the universe's infancy, potentially witnessing the moment the first stars switched on and burned away the cosmic dark ages. Here on Earth, immense particle colliders will continue to recreate the conditions of the Big Bang, searching for any subtle crack in the standard model that might point toward dark matter or even hidden dimensions. Our solar system becomes a laboratory for the question of life. Rovers will drill into the Martian subsurface, seeking fossils of ancient microbes, while spacecraft will fly through the icy geysers of Enceladus, tasting its hidden ocean for the chemical signatures of biology. Each mission is a direct response to a fundamental uncertainty we have explored, and perhaps most profoundly, the effort to unite gravity with the quantum world might be tested not in a massive machine, but in the quiet of a lunar base. The Moon's pristine environment, free of Earth's seismic rumble and radio chatter, could provide the perfect stage for ultrasensitive experiments to probe the fabric of space-time itself, seeking evidence of those quantum grains or the faint ripples from the birth of the universe. With every new instrument, we do not just seek to close a chapter, we are writing the opening lines of a new one. The answers we find will inevitably birth new, even more baffling questions, reshaping our cosmic perspective in ways we cannot yet foresee. This is the endless, beautiful cycle of science, a journey where the destination is not a final truth, but a deeper, more wondrous mystery. From the ghostly tug of dark matter to the silent, overwhelming push of dark energy, these 30 cosmic riddles are not the edge of our knowledge, but the foundation. They are the fertile ground from which the next great revolution in science will grow. Every mystery we have explored, from the quantum foam of space-time to the great silence of the cosmos, is a testament to a universe that is alive with questions. Carl Sagan's beautiful words echo across the decades, reminding us that somewhere, something incredible is waiting to be known. This pursuit is more than just a collection of data points. It is a source of profound wonder and a lesson in humility. It reconnects us with that ancient human instinct to look up at the star-filled sky and simply ask why. We are part of a grand, ongoing story of discovery, where each answered question peels back a layer to reveal an even deeper and more beautiful mystery beneath. So we turn the conversation over to you. Which of these enigmas captivates your imagination the most? Is it the true nature of black holes, the search for alien life, or the haunting fine-tuning of the universe? Share your thoughts in the comments below. If this journey to the frontiers of the unknown inspired you, subscribe to keep exploring the cosmos with us. Thank you for joining this adventure through the biggest questions we can ask.